Welcome back to another Explainer. Okay, today we are going on a truly mind-bending journey to hack into the basic source code of matter. We're going to strip away the everyday world, zoom right past the cells, the molecules, and the atoms, and tear reality right down to its absolute fundamental building blocks. So get ready, because this is the ultimate quantum teardown.
It's arguably the most profound question we can even ask, right? What is the universe actually made of? Now, if you crack open a physics textbook, you might get totally intimidated by this sheer alphabet soup of subatomic particles. I'm talking pions, muons, neutrinos, kaons. It's a lot. But don't worry about all that. We're going to demystify it today using a really sleek logical map called the Standard Model. Think of it as our master directory for the entire universe.
But before we get into the map, how do we actually know all this stuff? Well, to reveal these hidden quantum layers, we rely on the massive CERN Large Hadron Collider. We literally have to smash particles together at nearly the speed of light. It's wild. These gargantuan high-tech particle accelerators basically act like giant microscopes, physically breaking atoms apart so we can examine the shrapnel and figure out exactly how the universe is wired together.
So, here is our system map for the quantum world today. We'll be booting up 5 key categories: the Standard Model system, leptons as the solo particles, quarks and hadrons, forces and messengers, and finally, the dark matter mystery.
All right, let's kick things off with Section 1, the Standard Model system, and how we actually categorize these particles.
The universe is divided into 2 fundamental camps based on a property called quantum spin. On the left, we have fermions. These guys have half-integer spin and obey something called the Pauli exclusion principle. Basically, fermions are your solitary particles. No two can occupy the exact same quantum state. They take up space, which is exactly why they make up the solid physical matter in your body. But then, over on the right, we've got the bosons. They have integer spin, and they completely ignore that exclusion rule. These are the force carriers, and they absolutely love to pile up together in the exact same state.
And this brilliantly illustrates what happens when bosons actually do pile up. By cooling rubidium atoms, which act a lot like bosons, down to near absolute zero, they all collapse into the exact same lowest energy quantum state. It creates this stunning 3D spike, which is a bizarre state of matter called a Bose-Einstein condensate. It's basically a macroscopic demonstration of quantum rules happening right before our eyes.
Moving right along to Section 2, leptons are solo particles that are totally immune to the strong nuclear force.
Now, looking at this slick directory of the 6 leptons, notice how neatly they're organized into 3 distinct families. Now remember, leptons are fermions that just do not interact with the strong nuclear force. In our first family, we have our familiar everyday electron, and it's paired with its incredibly elusive zero-charge partner, the electron neutrino. Then we step up to the heavier families. You've got the muon and its neutrino, and finally the massive tau and its neutrino. And those neutrinos, man, they are like literal ghosts. They have almost no mass and zero electric charge, making them nearly impossible to actually detect.
Okay, Section 3. Quarks and hadrons, and the weird world of fractional charges.
You gotta admit, physicists clearly embraced a bit of whimsy when naming these 6 quarks, or flavors. We've got up, down, charm, strange, top, and bottom. Now, this classification ultimately grew out of a mathematical pattern in particle physics known as the eightfold way. But I want you to look closely at the data here, specifically those electric charges. Unlike the neat -1 charge of an electron, quarks possess these completely bizarre fractional electric charges of +2/3 and -1/3.
So here is the crucial point. Those fractional charges, we never actually see them in isolation in our everyday world. They always puzzle together perfectly to form whole numbers. We call these grouped particles hadrons, and they come in 2 main types. First, baryons, like the proton, which are always made of 3 quarks combined. Think about it. A proton is 2 up quarks and 1 down quark. If you do the math, +2/3 +2/3 -1/3, it perfectly equals a neat whole number plus 1 charge. It's like a giant puzzle. Then on the flip side, we have mesons, which are made of just 1 quark and 1 antiquark.
Now, under normal conditions, quarks are permanently locked away inside these larger particles. But in collisions at the RIC facility, temperatures get so ridiculously extreme that protons literally melt, briefly creating a primordial quark-gluon plasma. For just a tiny fraction of a second, this actually recreates the extreme conditions right after the Big Bang. You know, that exact same explosive era that left behind the cosmic background radiation that is still echoing through our universe today.
Which brings us to Section 4.
forces and messengers, or what I like to call the software of reality.
See, particles don't just magically know they're next to each other. They have to communicate. Think of these messenger particles, which, remember, are all bosons, as the network cables or Wi-Fi signals constantly pinging back and forth between matter to keep everything running. The electromagnetic force uses massless photons to hold your atoms together. The weak force, which is responsible for things like radioactive decay, communicates via massive W and Z bosons. And the strong color force, the actual glue holding the quarks together inside a proton, it communicates via, well, aptly named gluons.
But for the longest time, there was a massive puzzle here. Why are photons completely massless, but those W and Z bosons are incredibly heavy? Well, the answer is the Brout-Englert-Higgs field. It's this invisible field that permeates absolutely all of space. As some particles push through this field, they experience drag, and that drag is exactly what we measure as mass. And the quantum manifestation of this field? That's the famous Higgs boson. Confirmed in 2012 at CERN, the Higgs boson was literally the final missing piece of the Standard Model puzzle.
All right, finally, Section 5, the dark matter mystery in the universe's missing mass.
So here is the truly humbling truth about everything we've talked about so far. Everything we just analyzed, every single quark, lepton, every star you can see, is standard baryonic matter. And that accounts for only a tiny, tiny fraction of the universe. Thanks to Hubble's law, we know the universe is expanding, and it's being driven by two unseen phantoms. The first is dark energy, which is literally pushing the cosmos apart. The second is non-baryonic dark matter, which is holding galaxies together. Dark matter doesn't emit light, it doesn't interact electromagnetically. We only know it's there because its massive gravity pulls on the regular stars we actually can see.
Now, we do actually know of one particle that acts a little bit like this, the neutrino. Remember those ghostly leptons from earlier? Well, we know the universe is absolutely flooded with ancient neutrinos left over from the Big Bang. Billions of them are ghosting right through your body every single second, leaving zero trace. But here's the catch. Even their combined mass isn't nearly enough to explain the immense gravity of this whole dark matter mystery.
The Standard Model is an absolute triumph of human intellect, yet it only maps a tiny sliver of the cosmos, which leaves us with a haunting final thought. If it's not quarks and it's not neutrinos, what unknown fundamental particles are lurking in the shadows? What invisible force is passing right through you, right at this exact moment as you watch this explainer, silently holding the universe together in the dark? Keep wondering, keep questioning, and I'll see you in the next explainer.